So we've talked about simple harmonic oscillators in general. What we want to do at this point is come back and talk about the three particular simple harmonic oscillators that we'll deal with this class. The first one we want to look at is the spring and mass system. And this is a linear simple harmonic oscillator in the sense that it bounces back and forth along a line. So if I have a mass that's attached to the end of a spring and bouncing back and forth, when it's over here at this location, there's going to be some spring force that's pulling the mass back towards equilibrium. And so let me draw the free body diagram for the mass. Spring force again pointing back to the left, gravitational force pointing down, normal force pointing up. Let's assume that our surface is horizontal. Let's assume that it's frictionless. And then what I'm going to do is I'm going to go ahead and use the coordinate system that says let positive x point to the right. That'll let me set up my Newton's second law equations. So what's going on in y simply tells me that in this case the normal is equal to the weight. And so what I'm interested in is the x equation. And I'm going to do something that's subtle but important for the way that we're setting this up. So just notice that in this case what I'm choosing to do is say I'm going to solve for the x component, whatever it is, and just let the sign take care of itself, as opposed to saying that I know the direction of the acceleration and I'm going to line my coordinate system up with that. So when I do that, what I get is that, well, the spring force points back in the negative direction given my choice of coordinate system. When I plug in, I know I can calculate the magnitude of the spring force as k times some displacement. And so for a positive displacement, the spring force is going to point back in the negative direction. When I solve this for the x component of the acceleration, what I get is negative k over m times x. And so the important thing to take away from this is that this is the form of an equation for an object that's going to undergo simple harmonic motion. So when we solve for the x component of the acceleration, there are three important things sitting in this equation. There's a negative sign sitting out front, there's some constant, and then times x. And so in this case what we're going to do is we're going to say that this constant k over m is equal to omega squared, where this is the angular frequency. So negative the angular frequency squared times x. So what I have here is I have a simple harmonic oscillator because I know that when I solved this equation I got something that had the form of an equation for simple harmonic motion. So let me take that equation, and part of what I can do is say, well, now that I know what omega squared equals, so if this is negative omega squared times x, and that equals negative k over m times x, well, that tells me that the angular frequency for a spring and mass system, so that's why my Sm here is sort of this additional subscript, that squared is equal to k over m. I can solve for the angular frequency of my spring and mass by taking the square root of k over m. And so notice that the angular frequency of the spring and mass system depends on two parameters, k, the spring constant, and m, the mass that you've attached to the end of it. Once I know omega, now I can come back and say, well, I know how the period relates to the angular frequency. So the period for a spring and mass system has got to be 2 pi over the angular frequency of a spring and mass system. And so this would be 2 pi divided by the square root of k over m. And so again, dividing by a fraction, I can flip that over. And I get that the period for a spring and mass is equal to 2 pi times the square root of m over k. So the thing to highlight here is that all of this information for the angular frequency and the period and how they depend on the parameters of my system came from basically being able to interpret my Newton's second law equation. So let's look at the second example that we're going to have. So the second one's a simple pendulum. And a simple pendulum is an angular simple harmonic oscillator because instead of bouncing back and forth along a line, a simple pendulum swings back and forth through some angle. Now what makes it a simple pendulum is the fact that you can act as if all the mass is located at the end of the pendulum. So basically we can act like this is a massless string and all the mass is effectively down here, and we can treat it as if it's a point particle. So you got a massless string, and that point particle we end up calling the bob of your pendulum. So if I draw the free body diagram of the bob, there are two forces acting on it. So there's the gravitational force pulling it down because it has mass. It's not in contact with any surfaces. So the only thing left is that there's this tension force that acts back along the string. Well, because this is an angular simple harmonic oscillator, I know that I want to set up the rotational version of Newton's second law. And so the rotational version of Newton's second law says I need to pay attention to what my pivot is so I can calculate the torque about that pivot and make sure that I use the moment of inertia about that pivot. When I think about calculating the torque, again, if I've got positive angles when I pull my pendulum out in this direction, here's my pivot, here's the position vector for both of those forces because they both act on the bob. Well, it's easy to see that the tension force, because it lies along the same line as that position vector, it generates no torque about this pivot, so the only thing that does is the gravitational force. And so I can set up my rotational version of Newton's second law, the net torque equals I times alpha. And again, I'm going to leave this in terms of its z component. The net torque is equal to, my right-hand rule tells me that this torque points into the page. I said positive z was out, so I need a minus sign. The length of the string is the length of that position vector, so there's my L. The gravitational force, that's the magnitude of the force acting on it, and then the angle between those two vectors happens to be the angle theta that I've pulled my string away from horizontal. So here's my net torque, and that's got to equal I times the z component of the angular acceleration. Because I can treat the pendulum bob as a point mass, I know that its moment of inertia is going to be given by the mass times this perpendicular distance from the mass to the pivot, and that's just the length of the string, and that gets squared. So I've got ml squared times the z component of the angular acceleration. So here's what I get when I set the rotational version of Newton's second law. When I solve that for the z component of the angular acceleration, what I get is negative g over L times the sine of theta. And so the important detail here is, well, the sine of theta is not theta unless theta is a very small angle. So if theta is small, then theta in radians is basically about the same thing as sine theta. So what we have here is we have what's known as the small angle approximation that says if we keep theta small, so don't pull the pendulum way up here and let it go, but if you pull it out to about 10 degrees at its maximum and let it swing back and forth, then your small angle approximation holds, and then you have an equation that says that the angular acceleration z component is approximately equal to minus sign out front, you got a constant sitting here, times theta. That is the form of an equation representing simple harmonic motion. And so I can take my omega squared and figure out what the angular frequency is for a simple pendulum. So in this case, for a simple pendulum, I get that omega squared for a simple pendulum is equal to g over L. So omega is just the square root of g over L, where g again is the gravitational acceleration and L is the length of the string. The thing to notice, this does not depend on the mass. So you can put whatever size mass you want at the end of that pendulum bob, and as long as you can act like it's a point mass at the end of the string, the physics of this doesn't care about what that mass actually is. Well, once I know the angular acceleration for a simple pendulum, again I get the period for a simple pendulum by taking t equals 2 pi over omega. The third simple harmonic oscillator I want to look at is a physical pendulum. So again, a physical pendulum, the difference between a physical pendulum and a simple pendulum is I can't pretend like all the mass is sitting down here at the end of some massless string. Here the mass is effectively smeared all along the length in some fashion, but I can't just treat the mass as if it's a point particle. In that case, it's a physical pendulum, but I'm going to go through the same process, right? I'm going to pull it out, I'm going to let it swing back and forth, and so I want to draw the free body diagram of the pendulum. There's some normal that's exerted by the pivot here as it swings, right? Something holds it up here. And then again, gravity acts on the center of mass, pulling it straight down. Well, the pivot is where that normal force is exerted. So again, I know that this normal won't exert any torque about this pivot point because it acts at the pivot. So I'm left with simply the torque due to gravity in terms of thinking about the rotational version of Newton's second law. So again, I can set up that rotational version. I know I need the rotational version because this is swinging back and forth through some angle instead of moving back and forth along some line translationally. And so in this case, what I get is negative h times the gravitational force times, again, sine theta when I think about the angle between these two vectors. Where's the h come from? When you think about the parallel axis theorem, h is the distance from the center of mass, where gravity acts, to the pivot that you want that's not at the center of mass. So that's why this distance here has to be h. The gravitational force is just mg, so what I get is negative mgh sine theta is equal to I times the z component of the angular acceleration. Again, I'll solve that for the z component of the angular acceleration. I get negative some big constant times the sine of theta. And so again, if I make my small angle approximation, that tells me that the z component of the angular acceleration is approximately equal to negative omega squared, whatever that constant is, times theta. Because again, it's small angles, theta in radians is approximately the same as sine theta. So once again, I have an equation for simple harmonic motion, and I can use that equation to calculate out what the angular frequency and period must be for a physical pendulum. The angular frequency for a physical pendulum, again, omega squared is equal to whatever this big constant is between the minus sign and the theta. In this case, it's mgh over I. And so that means that the angular frequency for a physical pendulum is the square root of mgh over I. H is the distance from the center of mass to the pivot, and I is the moment of inertia about the pivot. And the thing to remember is I cannot be the moment of inertia about the center of mass. So if you try to make your object pivot about the center of mass, because that's where gravity acts, you'll never have a torque. So because you need the torque due to gravity to cause your pendulum to swing back and forth, you're always going to need to use parallel axis theorem to calculate the moment of inertia for your physical pendulum. Once I know what its angular frequency is, simple enough to calculate out the period for a physical pendulum in terms of its physical parameters. And so in this case, that's going to be 2 pi times the square root of, the I goes on top, over mgh. For all three of the simple harmonic oscillators that we're going to deal with, spring and mass system, simple pendulum, physical pendulum, we now have a way to calculate out what the angular frequency of each of those is and what the period of each simple harmonic oscillator is based on the physical parameters of each system.